area. But I guess this is a better example because I can actually make it. Here's the unit circle, right? Now you're already going to tell me the answer is a square. Good. Ah, beat you to it. But there are uglier problems. But anyway, this is a good warm-up. So suppose you want to inscribe a rectangle inside this disk, x squared plus y squared equals to, well, less than or equal to 1, really, right? The disk is just, we add an inequality if you want to be fussy. So, all right, so if this is 1 point right here, 1 point on my rectangle, then what's the rectangle look like? If it's inscribed, that means that all of the corners of it are actually on the circle. That's what inscribed means. So what's the area? That's a very bad picture. Those should be like symmetric, you know. What's the area of this? XY would be wrong, but a popular wrong answer. If you watch the video from last year, you'll find you have good company. Same wrong answer was given last year. It's what's that? Yeah, 4, right? Yeah. And I think last year is like, well, I'd minimize xy. If I maximize xy, then I multiply by 4. And I said, well, that's great, but what if you forget to do that, and you give me a fourth of the correct answer on the test? That's not going to be much consolation to you that you had the right idea, but you didn't write down. So yeah, 4xy. That's the objective. Maximize that. So here's our f. What's our constraint? Well, the constraint is what? X squared plus y squared equals to 1. I suppose I could make it more exciting by trading my circle for like an ellipse, right? Then you wouldn't be able to guess the answer quite so easily, right? If I say maximize the area of a rectangle inscribed inside an ellipse, then symmetry alone wouldn't maybe tell you the answer, right? The reason you guys know it's a square is because there's really no difference between x and y in this problem, right? So the answer has to respect that xy interchange symmetry. That leaves us with a square. And that's not a wrong way of thinking. In fact, that's a fantastic way of thinking. That's better than what we're doing right now. Important thought process, actually. But that's actually also not really the focus of this class. All right, so great. So nabla f equal to lambda times nabla g. What does that give us? So our objective function, we got ourselves a 4y, 4x equal to lambda, and then you got yourself a 2x, 2y. So that tells me that 4y equals to 2x lambda, and also that 4x is equal to 2y lambda. And then, of course, we also x squared plus y squared equals to 1, right? So there you go. There's our, we got to solve those. Got to solve those Lagrange multiplier equations. Let's see here. So, you know, lambda, you can basically assume lambda is not equal to 0 is decent, is good assumption. Why? If lambda is equal to 0, that means if lambda is equal to 0, that means that the gradient of f is 0, right? Which means this whole discussion breaks down anyway. And pragmatically, we'll actually pick up on those kinds of points in our looking. Where is local mins and maxes, by the way, guys? those are going to be where the gradient of f is equal to 0. So, I mean, pragmatically speaking, you're going to pick up on those points when you're looking for local mins and maxes. If you find one on the edge, that's going to be a place where the gradient of f is 0. So if you're willing to kind of extend your search to include such points in part 1, you already get those. Anyway, my point is, you can let lambda be not 0. You don't really lose much. If lambda equal to 0, that's a point to worry about, is my larger point. But if lambda is non-zero, then we can do what? Yeah. Let's see here. Oh, I don't know. Let me just write it down. Sorry, I'll get with it eventually here. So we've got what? We've got x lambda equal to 2y. And we've got y lambda equal to what? Two x, yeah? How about this? If xy is not equal to 0, right? Then we can divide the equations above, right? And that will tell us that x lambda over y lambda equals to 2y over 2x, which would tell us what? Which would tell us what? Right. It would tell us x squared equals to y squared. Which, by the way, would tell us that x squared minus y squared equals to 0, which would tell us that x plus y times x minus y is equal to 0. Or getting to the point, y is equal to plus or minus x is the sort of takeaway from that. By the way, if x is equal to 0, it's a reasonable... Notice that either x equals to 0 or y equals to 0 forces y equals to 0 and x equals to 0. I mean, if I put x equal to 0 here, that forces y to be 0. Right? If I put y equals to 0, it forces x to be 0. So either one of the coordinates being 0 forces the other coordinate to be 0. And we can't have 0 and 0 as a solution. Why? It's not on the constraint curve, right? It's x squared plus y squared has to be 1. Origin doesn't solve that. Origin's not on the unit circle. You know this. So this is actually not a limiting assumption. This is a reasonable assumption for the solution. X and y non-zero. And that gives us this, which then gives us what? X squared plus or minus x squared, right, equals to 1, aka 2x squared equals to 1. Therefore, x is equal to plus or minus 1 over root 2, and y is equal to plus or minus 1 over root 2. In short, you get the following solutions: 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2, and both minuses. So there's the solutions, all 4 of them. So which one of those 4 solutions gives you the answer? So this goes back to how the setup of the problem, right? When you find this problem, it does not come to you with the picture of the circle and the square rectangle drawn in it, okay? You guys have to make that up. You have to think of that, right? And so when you think of that, part of your thought process should be x and y. I'm going to put them in the first quadrant because I want x and y to be positive. I want them to correspond to the half of the length of the rectangle that I'm inscribing, you know? So only one of those 4 solutions we found is physically reasonable, given the setup. Yeah, the first one. Because x and y should be positive in my setup. Which, you're vindicated. There you go. There's your square. X and y are equal length. Right? And so the maximum area that you can give to a rectangle inscribed inside the unit circle is, in fact, the square that has area. So the a max is what? 1 over root 2. 1 over root 2 times what? Times 4, right? So we got 2. What are the dimensions of that rectangle? It's 2 over root 2 by 2 over root 2, right? Because twice x and twice y are actually the length and the width. Any questions? Let's look at a three-dimensional problem. We solved this before, but we'll solve it a different way now. So there are endless word problems that you can come to, building a soda can of optimal dimension, or packing a box that, you have different costs for different sides, and, deleted or included top to the box. And you can play these games setting up cost functions and min-maxing, and they're interesting problems. But most of my examples tend to just be based on just direct geometric stuff, because I think that's oftentimes more than enough for you guys to chew on. So here's another one of those. You got a plane. We solved this problem before. The plane is, I don't know, x plus 2y plus 4z equal to 7. And I've got this point up here, say, I don't know, 8 to 4, right? And then the question is, what point on the plane is closest? All right? Now, what's the fastest way to solve this? You already know. Yeah, find the normal line and find the point of intersection. Let me show you that Lagrange multipliers gives you the same solution method, all right? So what we're trying to minimize here, our objective is to minimize the distance, right, from this point to that off the plane point. So find closest point, right? So we could do just direct distance, but here's the thing: is distance is a drag because it's got a square root, right? So if you're asked a question about geometry, you should always try to minimize or maximize the squared distance, because that's polynomial, and trust me, that's better, right? So we do x minus 8 squared plus y minus 2 squared plus z minus 4 squared. That would be my objective function. This is my g, right? That's my constraint surface. And so we calculate the gradient of f equal lambda times the gradient of g. What's that give us? That gives us 2 times x minus 8, 2 times y minus 2, 2 times z minus 4 equals lambda times the gradient of g. Well, the gradient of g is the normal, right? So this gives us the equations x minus 8 equals to lambda over 2. Let me solve all of these for lambda, actually. This gives me 2 times x minus 8 equals to lambda. The second one gives me y minus 2 equals to lambda. The third equation gives me z minus 4 divided by 2 equals to lambda. So you can put these together, right? Like this tells me that 2 times x minus 8 is equal to y minus 2. And these two together tell me that 1/2 z minus 4 is equal to y minus 2, which these two put together give me then that 2 times x minus 8 is equal to z minus 4 over 2, which will relate x and z for me, right? So I've got 4 times x minus 8 equal to z minus 4, which gives me 4x minus 32 is equal to z minus 4, which is to say that 4x, well, let me solve for z, right? Z is equal to what? 4x minus 28. Then what's my y? This tells me that y is equal to 1/2 of z minus 4 plus 2, right? So then, we've got y, right? We've got z. So you take this star, you take this star star, and you take both of them, and you put it up into here, then you've got an equation just for x, right? So it gives us x plus 2 times 2x minus 14, plus 4 times z, which was 4x minus 28, equals to 7, which gives me what? What's 4 plus 16? 21x equals 7 minus 28 plus 4 times 28, which is what? $112? So what's x equal to? I guess 112 divided by 21, which is what? I mean, it's that. So I probably made a mistake at this point, but I wanted to show you that you can solve that kind of problem with Lagrange multipliers as well. Even though this is a good example of a problem which common sense will tell you that there is a minimum, right? You kind of see that geometrically. Is there a maximum? Is there a maximum distance for a point on the plane relative to the point off the plane? Certainly not, right? So, anyway, thanks guys. I will give you back your tests. These are in alphabetical order.